be like different exams, and one that we just had raised few weeks back. Any case, let's get started. Let me share the screen. Right. So what were we doing last week? So the last week we were trying to understand algorithmically what makes the algorithm of finding the minimum number of edges to get a connected graph work, right? So the algorithm for minimum connected graphs. Obviously, starting with just points. That's the context in which we are doing, which we started. So we had n points. We had 1 minute. Right. We had n points, and we know how to get a connected graph which uses the minimum number of edges, right? And we know the way to do this was just at each step add an edge so that you don't get a cycle. We reduce the problem to that and so on. We saw the theory side of it. Okay. So the key was that the crux, what made everything work, was that all maximal, okay, all maximal graphs with no cycles, because this was the form in which we were finding our result. We were not trying to find a minimum directly. We were trying to find a maximum of something, right? And we did that by finding maximal graphs with no cycle. All maximal graphs with no cycles have same number of lines or same number of edges. And obviously this is same as minimum connected that we know, right? But this is what we were claiming, right? And we have seen this in different ways, but see, I'll just recap one small thing here. Maximum with no cycles. If you want the maximum graph, maximum here means a graph with most number of lines, but still not having any cycles. So just avoiding cycles. This is obviously equal to minimum connected, or we should rather start using the word tree from here. This is just the language for it. Just tree is a good name and it just simplifies things. This we know, but we did not find the maximum. We did not directly find the maximum, right? Why? Because we were doing the problem algorithmically, and when you do something algorithmically, you do not find maximums algorithmically so easily, right? You find maximals. Now, what is maximal? Obviously, we know that maximal is something that cannot be improved upon. So at each step, you're doing something, you making a choice, and you get something that cannot be further improved. Means you cannot add any more edge in that, right? But there's no claim that in general we do not know if that will be the maximum, but in this case it was, because of this thing, because all maximal graphs with no cycles have same number of edges, and we know the number n-1. And this thing we have proved theoretically. We proved this, and this is what made our algorithm work. Okay, so the lesson from here should be that, I mean, usually when you want to do algorithm, then you'll do maximal. Okay, and then you want to show that will be the algorithmic side. How you will do might be greedy, might be some other method. This was greedy. And then theoretical result, which you have to prove or use or whatever, is that maximal is same as maximum. Okay, so this was the summary of what we had done. Now today we want to see this thing, this fact of all maximal graphs with no cycles, obviously on n vertices, have the same number of edges, we want to see this in a different way, okay? A different perspective, which will be essential. Well, it's not essential, but it's a very interesting property, and it is in some sense very, very important for the weighted case. Okay, that's why we'll introduce this result. A different perspective. Maybe I'll just call this star. Star. Okay. So before we go into that, are there any questions? No questions. Okay. So we want to see this in a different way. And the way we want to do this is it's called I'll just say a name so that when I describe the method, you can relate to it more. Okay. An exchange technique. Okay. This technique is very powerful. This technique, we will be using the same technique we will be using for interval scheduling problems, which we started in one of the classes. So they are used there. Exchange tech. So this is another kind of way in which greedy algorithms are proved to work. The one way which we have seen is that the greedy algorithm always stays ahead. But here we will see this. We'll use this technique in those cases. And this exchange technique in combinatorics is also goes into what is known as the bijection principle. It's not exactly bijection principle, but it is sort of like somewhat like that. We sort of pair things from two different places to show that things are equal without actually counting them. This is a very, sometimes it just appears so miraculous, right? So this is used in a lot of places, and it's used in many other contexts also, but this is what we will use, an exchange technique. Why? What exchange? Exchange between what? So again, when I said all maximal graphs with no cycles have same number of edges. So what we will say is we will take two maximal graphs with same cycles and we will compare, we will exchange some things between them and show that they have same number of edges. Okay, so here I will have a G1. So this is just for, this is not a picture, it's a picture of the concept. It's not a picture of some graph, but it's just a picture of what I'm trying, just the concept behind it, or the meta picture. We have two graphs. These are very general techniques, so we should pick them up, try to pick them up and understand them in this way. We'll have two graphs, G1 and G2, and both are maximal graphs with no cycles on n vertices, of course. Okay. So let me write here, G1, G2 are maximal, no cycles. I could have just written G1 satisfies star, but let's write more. And slowly we'll reduce the words as we get more comfortable. I'll get to know from the people. G1, G2 are maximal, no cycles on n vertices, of course. Let me write that also. Okay, so we have two graphs with that property. And you, as I said, this technique is very general. After some time, you will be looking at two sets of polynomials and doing some exchange. You'll be looking at two sets of vectors, and in this same technique works. Okay, so it's very, very important technique. And you can just understand from the very elegance of it that it will be. So let's just roughly draw it. Okay, roughly meaning that just some points. Let's keep the points on the same spatial arrangement. Something, yeah, something. Wait, is one of them a point or a dot on my screen? No, these are all. Okay, so this is good. Okay, so we have two. Okay, now both of them are maximal with no cycles. Let us actually draw one of them. So I was saying we will not, but let's just draw. Okay, maximal. Yes, both have n vertices. That is obviously important, right? Otherwise they will not have same number of it. So we have the same number of points to start with. Okay, that is, as you can understand, that's a natural condition, because for a different number we will again do in a different way, sorry, in the same way, right? Yeah. Mhm. They will be different, that is the point. Yeah, they will be different. Okay, they will be different. Different kinds of lines will be here, and here different kinds of lines will be there. They are different graphs, right? Because you see that was the point, that you can get maximal graphs with no cycles. There are many such graphs, right? There are many graphs like this which have no cycles. I mean, there will, Sunday's class will try to count them also, or some later time we'll try to count them. Okay, for example, the easiest one obviously, which all of you know, is just a cycle. You can draw many. You can just draw a star, right? You can take a point and you can just draw some sort of a rays only from one point. So only one parent and all children. There are many ways to do this. We want to show that, or we want to see in a different way rather, because we all know it, that they have n-1 edges, because we know that. But still we want to just see it in a different way through a very dynamic exchange manner, and that exchange manner will actually tell us something more than just, yeah. So let's just draw randomly some. So we just want it to be having maximal with no cycles, and we sort of know that it's kind of just connected, right? That's the same thing as connected, basically, that we have also seen. But yeah, so this is okay. This doesn't have any cycles, and it is maximal in the sense that you cannot draw another line. If you draw any more lines, so this line should be, this is a line, yeah. If you draw any more lines, this will have a cycle. So this is maximal with no cycles. On this side, let me not draw all the lines, because if I draw all the lines, then you can see that there will be same number of lines on both sides, and then that's what I want to prove. Right. So I will not draw a picture on this side. Let's just draw one line, let's say, which we'll be interested in exchanging. And here, maybe there are some other lines and dot, 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 what? No, let's not put dot, 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 something like this. Okay. Both are maximal, same number of vertices, and they don't have any cycles. We want to show that they have the same number of lines in them. And what is exactly that number is not important, but as you can understand, that number should be 3, 4, 5, 6, 7, 8. 9 points, 8 lines. Okay. So what is the exchange? Okay. We will show that lines, or we will, in this first situation, we will show that number of lines in G1 is more than equal to number of lines in G2. Okay. G2 is not, I've not completed it intentionally. Okay. Because if I complete it, then you will see that it will also have 7. If I just draw something and I try to complete it, so this is not allowed. Then you see it's always also a bit. So then there's nothing to prove. But if to prove this for general n, right, and we want to prove for two general maximal graphs. These are two special cases if I draw them. That's why we don't want to completely draw. Okay, so just maybe something like this. We'll show this, and then we'll reverse. You can use the same argument to show the other way. This is because they are the same. They are both maximal. They are not same, but they have the same property. So we'll show this first. And the way we will do this is via an exchange type argument. So let's take a second break and do it while I erase all this.
Excuse me, can you
Yeah.
just repeat what the number of lines in G1 is greater than equal
We are trying to prove that. Yeah. We are trying to prove that if there are two maximal graphs with no cycles, then they should have same number of lines, right? And we'll do that in two steps. Essentially, they are same, but two steps which are very similar. And that will be that we'll show that one side has at least as many as the other side. And then it will be true in the other way around, and they'll become equal, right? So yeah, and this is this is a way to show things are equal when you don't know the number of. Here we are pretending we don't know because we actually know, but we just want to see it in a different way. So this is the thing. And then what is the exchange? So in this case, when you want to show that G1 has more lines than G2, we will pick an arbitrary line. So the way we do this is we will pick an edge. Let's use the same language. I pick a line in G2, any line. Okay, just pick a line in G2 which is not in G1, which is okay. So the vertices are, I have drawn them in the same way so that you can see that they are just same, but the edges are different. Okay, which is not in G2, which is not in G1. Sorry. Right. I want to first do this. How do I do? How do I pick a line which is in G1 but not in G2, which is in G2 but not in G1? Sorry. This is one example. Okay. I'll pick that line. What will I do? I will place this line. So I picked it up. Now I will. Sorry. Ari Baba. Okay. 1 minute. See, if you take a complement of G1, but then you have to take the intersection with G2. Right? That's exactly what I'm trying to do, but I'm trying to say it in a more concrete way. Yeah, that's right. You can just take G1 complement G2 and take the intersection and blah, blah. But I'm just trying to show it more concretely. So what we do is I'll just show one step. So you pick this line and you place it here in this graph. Okay. I've picked a line from G2 and I placed it in G1. And then, so what has G1 become? G1 may, let's call this E. Okay, I have added a line E which was not in G1. This is just a very traditional notation, so I'm just using it. Okay, in G1 I'm adding a line which was not in G1, and now it has a cycle, of course, because it was a maximal graph with no cycles. So what I will do now is I will delete a line from G1. Okay, next be delete a line from G1, obviously, such that we still get a, okay, here I should have said add it to G1 and then delete a line from G1 such that uh, it is still a connected graph, or still graph with no cycles and maximal, still of same kind. And obviously I can do that. I'll just delete something from this triangle, say this one. So maybe I should have called that F, and now F is gone. Okay, so there was a F here, or maybe let's just keep the F, but let's just cross it maybe. So I have done. Okay, so in some sense, I have absorbed one line from G2 in G1. Right, I mean, I had to shed one of my lines, but I've absorbed one line. And now this new graph, this is a new situation now, right? It's G1 plus E minus F. It's not G1. It is G1 with one edge added from G2 and one edge of its own removed. Okay, but we have absorbed one edge and removed one edge from G1 and absorbed one edge from G2. In this way, and see why, so this looks like a very trivial thing now because we are doing it in such a concrete case and we have spent time in understanding this, that when you add a line, then you get a cycle, and on that cycle, there is something which you can obviously remove, and still you will have the same kind of graph, which will be maximal, connected, minimal connected, maximal with no cycle, all those things will still be preserved. Okay, so this is still a tree. This situation is still a tree, but I have absorbed one line from G2. In this way, I can keep absorbing lines from G2. In this way, I can absorb, I'm not writing that part. You guys, now that's your work to do it, okay? In this way, I can absorb one by one all the lines from G2 which are not already in G1. Those which are there, that's already, G1 already has them. But those which are not there, it can still absorb them, right? So what does that mean? It means that G1 should have had at least that many lines as G2 had. Is that good? Yeah. So all this will imply, after you keep doing this for other lines and absorbing them in G1, this will imply that G1 will have, just using this wrong notation, but G1 will have at least that many lines as G2. That's what we'll be showing in the end, right? If you run this argument. There are still a few traps in them that you will realize if you actually try to write it carefully. There are some traps which I have not explained, but that I'll leave for you to actually discover when you write it. Okay, that what's the guarantee that you're not removing the line that you added at some point and so on, that you have to think about. Okay. But is this intuitively making sense? And at least in this execution right in front of us. Yeah, this is the exchange. You have taken the vertices of G2 and sort of putting them in G1 one by one. Okay. And this is a very powerful property of trees also, right? That given a tree, you can bring a line which was not in the tree and remove a line from that cycle and still get a tree. Just a slight perturbation, slight change. Right? These things are tending towards that there should be many trees, and there should be there is a very interesting exchange thing that goes. Right? So, any questions? Yeah. Hmm.
If we had a function c1 which was not in G2, which was a for equal equal,
Hmm.
now when we are removing an edge from G2, should we remove an edge from G2 or should we not?
Yes. So that is my point. That you have to. That was a trap which you have to think about. Yeah. More than that also, what if you end up removing an edge that you had added at some point, right? Then you'll end up in a loop, right? The algorithm will not terminate. So you have to think about how you can avoid it. So the answer to that is there will always be an edge in G1 which you can remove, which is fresh, which was in G1, only in G1. Okay.
From G1 and G2 we can prove the same.
No, then there is nothing to prove, right?
No, I'm just saying that if we move to C1 so it will work in G2 too.
Yes. It will still work, and because there are no cycles, right? Think about that. Yeah. I mean, if most of it is same, but few of the edges are not the same, then also you can show that there will always be something like when if you can show that whenever you pick an edge from here and you put it here, you can always remove. So you'll have a cycle, but then there will be something on the cycle which will be solely belonging to G1, which you can remove. Then you will be done, right? That was your question was. That was I was just talking about the trap. That is a trap. Okay. How can you? But the thing is that you can always do this. You can whenever you take an edge from G1 from G2 and push it in G1, there will always be something in G1 on that cycle, obviously, which you can remove, which was not in G2, and that is very clear, right? That is very clear also. Now that I've repeated this statement two times, it's just very clear. So let me say it. I mean, suppose this edge was there, right? Now, if you put this edge, if you took this edge and put it here, right? And then you say that, and then I am claiming that there will be something on this cycle which was only in G1, so that I can continue my process only in G1. If you say no, what if all of it was? What if G1 and G2 were so same that all these were in G2 also? But that cannot happen. If all these were in G2, then G2 would have a cycle, right? So there is something in G1 which was only in G1. Okay. So, but those things I want still, you have to still write it. Okay. To write it. Okay. So take 2, 3 more examples, run it. You will see these traps and then you can write it. Okay. Is it good? Okay. Right.
Then in here it is it's the line
No, so actually I was slightly wrong in that handling of the word. Yeah. When you ask this question, you're right. So I used this exchange word in a slightly wrong way. Well, maybe it makes a little sense at least. But I used this, that's a very good question. I use this exchange word like you're taking edges from here and you're putting it here, and that's the exchange. That is right in some sense, but the actual exchange, both the sides is happening here. You are exchanging F for E, or you're exchanging E for F. No, you're exchanging F for E. Yeah. This is the exchange that you're removing. So from G1, you're going to G1 plus E minus F. This is the you're exchanging E for F or F for E. Get confused with. Yeah. That is the exchange. Okay. Okay. It's a very, very fantastic argument and very general argument. So this is used in some like the theorems we learn in hardcore linear algebra and such. There we use this. Okay. And like those are the only ways to do this, do some results. And so it's so nice. Okay. And yeah, and it starts with something like this, which can be just explained to anyone. I mean, you can just explain it if you explain it patiently enough, right? Okay. So are there any doubts? Okay. Okay, one at a time. Pragya, maybe you can finish first. Hello? Sorry, go on, go on.
So yeah, I was saying that can you show us the other example?
Yes, yes, sure. Let's actually do an explicitly an example. Yeah, yeah, I think that is good, right? Okay, and what was the other question? Someone was going to say something. Okay, so let's do this one. Okay, yeah, let's take an example where I explicitly do this. That's a good thing, right? To do. So let's take a graph random. I just want to take a very random graph. So this is a maximal, the red one. This is a maximal graph which doesn't have any cycles. Okay. On the right side, let's use a different color. Let's maybe green because green is going to come in, and the red will go. No, sorry. This is maybe something like maybe let's take this kind of graph. So you see these two are somewhat similar also. Okay, so you can see it. Let's start the exchange process. Yeah, myself I have never tried to execute it very properly, but in any case, so we can start with this. This looks like something that is not there, right? This one. See, if you are getting confused with the exact nature of the points, then you should number the points. That's always a good idea when you execute this. Okay, just number the point, then there will be absolutely. And see, theoretically speaking, you have to number the points. Okay, otherwise just this doesn't, because graph is not a drawing. A graph is set with 6 elements and there is a binary relation and like 1 comma 2 1 comma 3 1 comma 4 1 comma 5 1 comma 6. That's the relation on this side. It's just a relation with no conditions, no other conditions, if for those who have studied relations. In any case, you take this E and then you bring this E here. So let's actually bring it here, and let's actually delete it from here when we bring it here, right? Now, no matter how similar these two graphs are, there will be one of these will not be in G2. So G2 and G1, right? Otherwise, G2 will have a cycle. So it's all working out, right? That maximally or maximal thing we are also using, and no cycle we are also using. And sure enough, we have one. So we'll remove this. So I'm just doing it like this visually, not writing anything. Have this. What is the next thing to do? Well, it's just this one. This is the only one that's left, right? So we put it there, we put it here, and we remove it from here. Once again, this is just what should we remove? Which edge should we remove now from G1? Yeah, someone? Yeah, perfect, right? Just remove that, and that's it. You see, you have see, and you actually got that this new G1 actually became equal to what G2 was. That will always happen, right? So G1 went to G1 minus, oh, what was the first thing we removed? We removed 3 comma this. Maybe I should use the same notation. So minus, and also black color, minus this, plus we added 1 3. That was the first exchange, right? And what was the second exchange? In this, let me call this G1 prime. Then G1 double prime became G1 prime, and again we removed from this new G1 prime what we had removed. I should maybe write first they added one combinatorially, but it's okay. And we added 1 5. And you see this final graph was equal, became equal to G2, and this will obviously always happen. Just think about it, right? And this is it. You have exchanged, and we never will never end up in a loop. We will never. I never removed something which I had added at one point. So if I had added some edge from here to here, I didn't remove that, because if I do that, then I'll end up in a cycle maybe. Okay. Um, Uh, well, yeah, no, we should not do that. That's right. We shouldn't do that. Otherwise, you might be cheating. Okay. Okay. So then, is it clear, right, that number of edges that G1 had is at least the number of edges that G2 had, and then you can run it in the other way. I mean, you don't even have to prove anything like that, because then, because you have proved that if one of them is maximal, then this has more edges than this, then similarly this is also maximal, so this should also have more edges than G1, and so they should have equal. Okay. Is it good? Try to, but do more examples. If it depends on you, how comfortable someone is, they should do as many examples as they need to. Okay. Okay. And then you can, there's nothing to write really, but try to write if you want to. Okay, let's continue. So let me then not go to the weighted case today, otherwise we will not be able to do any. I want to do some more problems kind of thing. This is a technique, but also we should do problems more, right? A little bit more. So let me not go to the weighted case today. So those who maybe have to wait a bit more for the weighted case. Let's come to one of the questions. But this is also a question very related to trees only. A question which we had actually raised a few weeks back, and it's pending. So here is the situation. So let's say that you have, and we had seen this example, 6 vertices. Okay, we have 6 points. Okay, and we can make a tree in this, right? We can make a tree. Okay, a tree in, maybe let me call it T1, a tree T1. Okay, with obviously with 5 edges. I'll put it in brackets because it will have 5 edges. You can make a tree T1 with 5 edges. So it's like a network that you are laying. All right, you're laying a minimal network, the cheapest network sort of. Okay, which will connect. Communication can happen throughout. But now we are not satisfied with just this. We are asking, okay, we have built one set of roads. Can we build a set of bridges now above it? Okay, so the question is, can you, so making one tree is okay, very easy, made it. But can we now make another tree? Can we make another tree? And obviously, when I ask this question, I mean, which don't use these edges. Okay. Can you make another tree? I'll just say disjoint. Okay. Disjoint is understood, right? From T1. It's a very natural question to ask. Yeah, you can find it in some exams, maybe from disjoint from T1. But this was a question which I just naturally asked last few weeks back, and then from T1. Can we make another one? And how many such can we make? What's the maximum number? What's the maximum number of trees we can make? That's a very interesting optimization question, right? What's the maximum number of minimum connected graphs, okay, or maximal graphs with no cycles, or just trees? Okay. So one doesn't have to always, you can just think of trees any way you want to think of. Okay, it should just be correct. You don't have to always carry all the baggage together at the same time. When it's needed, it will automatically come to the table. So let's just keep it easy and just, yeah. What's the maximum number of trees on 6 vertices? Such that, so when I say maximum, I mean disjoint. I should maybe should have put this question. I maybe should have put this question as what's the maximum number of trees we can fit, on 6. So, yeah. In this situation, can we make another tree? Yeah, in this particular. No. So initially, yes or no, because initially, obviously, we have to answer this question for starting with empty. That is one question. But currently, I'm just focusing on this smaller question where we have to just make yes on top of this. On top of this, can we make another tree? Certainly no, because I've made a very hmm? No, right? Yeah, yeah, actually we cannot. We cannot make a tree not because of cycles only, but because I've just used up all the power of this city. Right now, if I make another thing, then another tree, then I cannot use this vertex. Right? I cannot. I'll draw a line from it because I've already used all of it here. So obviously our underlying conditions is that, look, your tree should, or your graph, that you the tree that we're asking for should cover the graph. It should have all the vertices on it, and these are called spanning trees, but that's the context in which you're using it. Okay, so the tree that you're trying to draw, they should cover the entire graph. Otherwise it doesn't. Yeah, spanning tree. And also from between 2 points I cannot draw two lines. That's another condition. Otherwise you can just make an infinite number of trees. That's again not an interesting question. Yeah. So yes, I cannot do. So it means that we have to draw the trees wisely. That was just the lesson, just as I was trying to say, because when I was also trying this, yeah, I realized that. So yeah, now we are back to the original question. What's the maximum number of trees we can draw on 6 vertices? What's the maximum number of trees we can fit in on 6 vertices? So I'll also number the vertices so that someone is saying. Yes, yes, yeah, obviously. In one single, meaning that, yes, in one single diagram. That's what I meant, that disjoint trees. So we have to draw one tree and we have to draw another tree on top of it, which doesn't use any of the edges from the previous tree. And then again, we have to do this. And how many can we do like this? Right? So I mean, I think you had given me a construction some weeks back, right? You only had given me. So yeah, it just comes if you experiment with it. Yeah. So this is one. Can we draw another one? Um,
5 to 4, then 6, and say 2 to 4 suppose that.
2 to 4. Okay, 2 to 4.
So then 4 to 6 and 6, so 6 to 1 and 1 to 3.
Yeah, and there are no cycles. Right. You see, so we have just put another tree. So this will also make the question more clear. We can put another tree, which is not using those edges. Really, it's about just asking the question in a simple language. So these questions are asked naturally, just framed in a complicated language in some very theoretical graph theory place. But if you can just frame it like this, and it's easy. It's just, and then we can just draw the remaining edges. Just that we should not get a cycle, so one must just take care. If I'm getting a cycle, just point it out. If you see 1, 2, 3, 4, 5, no. Yes, all is good, right? No, 1, 2, 3, 4, yes, all is good. Yeah, you see, so you see you get three, so three trees, and see, three is certainly the maximum. Can't get more than three, right? Couldn't have got more than three. It's impossible. So what does this suggest? I mean, obviously, we want to solve this question in general. We don't want to just do it for 6 or 8 or 10. So, what can we conjecture? What can we conjecture from here? Could we have guessed the number 3 right from the start? Or why 3? Okay, why? So, yeah, in the sense that Why did we get 3? Could we have foreseen that? Or could you, yeah, some sort of pattern, yeah, or some kind of bound, because yeah, let's think about that.
Just I mean, if you have n numbers, so there can be n tree.
Yes. Yes. At least when n is even. That's what I was looking for, right? So n vertices implies n by 2 trees. Now this is just a conjecture, okay? Because you don't know if this is hold will hold or not, okay? And that, yeah, that is still there. But let us just do this for n even, okay? Because then we are very clear. And the odd case, there'll be slightly plus minus one plus minus here and there. That's those are not graph theoretic issues, just number issues. So not a big issue in this, not interesting in this case. So we'll just do this. I will see if this is true or not. Okay? But this is just the right conjecture to make. So you have to just see when you're studying these topics, it's really about just doing spending enough time on small cases and then asking yourself the next natural question. So you made one tree, then you ask yourself, can I make another tree? And then how many? And then you make some small case, then you make a conjecture. So this is just I'm not really doing anything. I'm just making you guys ask the right questions. Just ask the right questions, and maybe with a bit of just seeing things in a bigger way and so on, you can just move forward step by step. Okay. Obviously, there are some languages things which come in, some terminology, some special techniques and so on, but it's mostly just about asking the questions. So we get this. This is a conjecture. But so what can we say? What can we definitely say? So maybe I should just call it the easy part. What is the easy part? This is another way in which someone could have approached the problem without even drawing anything. So those who like to think more calculation wise, computationally. So the easy part is that there are at most k trees. Is this so? Can someone explain me why this is true? Like this is just this is what will follow from what we just know already. K, obviously I mean k disjoint trees. Okay, k, and let me add another piece of adjective which will make it more precise. Edge disjoint trees. A more formal way to do these things is to make these definitions. So we'll define what disjoint family of graphs means, and then we'll use. But it's okay. If we understand it from here, I think it's just makes the journey more natural and easier. Edge disjoint trees. So edge disjoint means that they should not share any edges. T1 should not share any edges with T2. Just like this picture here, which we have. Beautiful picture. Yeah. So can we say how to say this? There are at most k edge disjoint.
So I will try to answer that.
Mm-hmm.
At most, we can see that there are like I don't want to use the term, but 62 uh, like edges we can draw at most. So we can see that there are 15 number of edges at most, and if each tree must have like 5 edges, then we can
That's right. Yeah, that's right. That is exactly what it is. Yeah, that is exactly what it is. So when there are when then there are 2k vertices, right? So when there are 2k, so that is just on grounds of set theory, on grounds of just basic numerical grounds, not even structural grounds, just numerical grounds. There cannot be more than k trees. Okay, so 2k vertices, yeah, 2k vertices imply how many lines can we make at most. So just try to show that you can make at most this many lines. Obviously it's 2k, choose 2 if you know, otherwise it's even more interesting. Just try to just, yeah, prove this. So when there are 2k vertices, there will be this many lines. because when you draw a line, you have 2k choices for the first its first point, and 2k minus 1 choices for its second point, and why you're dividing by 2, try to figure it out. It's a very straightforward thing. um Wait, am I making a mistake some? Yeah, this is right. Okay, so this means we have k times 2k minus 1 lines. So you have this many lines, right? So if you have this many lines and each tree uses, now just finish the argument from here yourself. Each tree will use 2k minus 1 vertex. Now this is something that you have already proved. Each tree will use exactly 2k minus 1 vertices. So obviously you cannot have more than k trees. Is this argument okay? Should I? Okay. So that implies at most k trees. This can also be said as basically there's something called the complete graph. The complete graph means a graph which just all the possible edges are drawn, and this is saying how many. This is asking how many trees or how many trees we can decompose the complete graph into. Okay, you can ask this question for other interesting graphs, but right now I think it would be difficult. And some of them are open problems, and some of them are just too hard or not too interesting, and so on. So this is what it is. Okay, 2k vertices, at most k trees is obvious, but just like we have been seeing that trees are very easily occurring objects, right? Trees look like a structural thing. Trees, they look like a structural thing. They look like something graph theoretic combinatorial, but they are somewhat closer to set theory, closer to just uh, being deducible from numbers or numerical information than one may initially think of. Okay, we have already seen this phenomena earlier. Just the number n minus 1 and no cycle decides a tree. Okay? All trees have the same number of edges and so on, right? So trees are very much, uh, they are structural, but still they are very simple. Okay, so if you get some bounds on some questions, for some questions based on trees, if you get some bounds numerically, based on just the counting and the numbers, then there's a good chance that that bound will actually be attainable. Here you have a bound k, and so that's based on that experience. I knew that this will be true. So I was 90% sure this will be true, and we can try to prove it. Okay, but this is the thing, that these are structural things, but they're very simple things. Okay, that's why later on when we do induction is done on numbers, just natural numbers. So you prove something in the beginning, and then you prove that if you have know something for k, then you know it for k plus 1 also, and then so it's true for all. That looks like an obvious thing, but that is an axiom. Okay, but it's for numbers. But because trees are structurally so simple, there is a notion of induction on trees also. So not induction on trees, but there is a certain kind of thing called tree induction also. Okay, so it's because all these things are just pointing, just again repeating this meta whatever statement, that trees are very close to numbers and they behave like numbers, just like the natural numbers are a string. Trees are not numbers because they're not so simple like numbers, but they are just the next thing to numbers, just the next thing to numbers. Okay, and this phenomena generalizes, like when you have something called a linear space, then that linear space, all you need to know about a linear space is contained in its dimension. That doesn't happen for more complicated kind of spaces if you put more structure. So those kind of things you'll see slowly, but yeah, but you can, this just helps you to make more mature guesses and so on. So now the question is, anyways, now we come to this, how do we prove such a thing? The more relevant question is how can we, and so let's say that this is correct. Let's assume that this is correct, because you can do this problem for 8 and then for 10, and you can see that it's correct, and so you'll be quite sure after that. Okay. So I'm just saying k trees, so this is correct. How do we prove it? How do you prove such statements? how to show there are exactly k trees. So it was very easy to guess the number k, but how do we show that there are k of them? So whenever there are even number of vertices, right? So I think just think about this. Okay, think about this. Let me just say the idea of what I think will work. Okay, and let's just see from how do you, knowing that on 6 you can, I should not have removed that diagram maybe, knowing that on 6 you can make 3 trees. So yeah, I'll have a tough time making this. Can 3 1 2 3 4, I need one more, so I make this, I'd use this, and maybe I should use this, right? And then the next one, so I'm just again remaking it. I should not have removed that, because I'll be using this. I mean, the point is that when you yourself do this question, when you try to make this construction for 8 and then for 10, then you will realize that how can I use the construction for 6 to do the construction for 8? Can I use that to do it for 10? If you're coding this, that's how you will do, right? You will write a, if you, uh, the problem for 2k minus 2, and then try to do something and make it for the next two. Make another tree for the, when you add two more vertices. So that's something that you will naturally arrive at when you do this problem. Try to do this for 8 and 10. 3, 4, one more edge. Here, sorry. Yeah, I think this is good. Yeah. Okay. Now the question is that, and this is something that you will just probably arrive at naturally if you do this yourself, is when you add two more vertices. Now you're trying to do the construction for 8. How can you just extend this? We want to be lazy. We want to just extend this construction and just do it for 8 vertices. So now I just want one more tree. I have put two more vertices. So this is the case for 8. This was the case for 6. I just want one more tree. How can I create one more tree? What's the most obvious way to do that? So we'll take a new color, then make one more tree. Pink. So a pink tree. Again, now that tree should, yeah, at least to start with, let's just think about that. Yeah. Uh, yeah. How? What is the construction? We'll name it one. Yeah. So let me name them. Yeah. Yes. That's right. Somewhat like a star, but we need to use 8 also, right? So we will, yeah, just on the basis of symmetry and so on. Well, this is not, hexagon is not a right way to draw. I should have but that all that you have to figure out when you write a proof, this and then you do this, right? You get one more tree. So are we done? Have we made the construction for 8? No, there's something missing. Yes, something is missing. Please see that this is incorrect. In a sense that, see, this tree, I have this pink tree is good. It uses all the 8 vertices, but now the other trees are not complete. They only use 6 vertices. I have to complete them, right? Right. I mean, so right. So think about how you do it. Now, this is just homework. This is easy. It's just easy in the sense that it's along these lines only. Okay, but just think about it. For example, for the blue tree, you have to also complete it. But you can again do that kind of even distribution and so on. Think about it. It's an interesting but easy construction, easier. Okay, and in this way, you can imagine, you can do it. Okay, so I'm not completing it. I just try to do it. It's almost complete. But any questions? Any questions? I think this was very interesting. So everything is clear. Okay. So again, I'll not go to the weighted part. Okay, today. Let's yeah, let me, so what should I do in this small time? Yeah, let me just put a question which you guys should just try. Okay. And this is a related question to what we were doing on Wednesday, but those who are not there, no need to worry because this is just similar. Maybe slightly better idea though they'll have those who were there, but will not make any difference. Okay, so this question is as follows. So we have a, just writing it in full details, more or less. So we have a cell phone company. Okay, because to decipher, just remove the garbage from the question is also sometimes important, and it's a good thing. I find it very hard sometimes. Get confused when there are so many details, and most of them are not important. That's the point. Okay, so anyway, so cell phone company provides service on 7 different frequencies. Okay, 7 different frequencies. Okay. 7 different frequencies, and we want to set up um, towers. Okay, so we have want to set up 100 towers. So set up, or rather I should say want to set up 100 towers in fixed locations. The locations are fixed. We are not allowed to change that. This will be important. Okay, so here it's also about the distance. The distance will be fixed. Well, in the end, it will not be about that, but yeah, 100 towers, 100 towers in fixed locations for this purpose. Okay. Now, obviously, the company has to ensure that 2 towers that are broadcasting on the same frequency are at least 100 kilometers apart. Okay. So 2 towers. 1 minute. Yeah. Okay. Broadcasting on same frequency are at least 100 meters apart. Okay, this is the thing, and the locations are given to you, the distances are given to you, let's say, as an input. I mean, you want to decide if, given these 100 locations, okay, so we have 100 locations, 100 towers we want to put there, 100 subjects, 7 classrooms, something like that. Also, you can think there are 100 towers and there are 7 different frequencies. Okay, and the question is it feasible? Is it is it feasible? So is it feasible for me to use only 7 frequencies? See, if I just think about it, if I have a lot of frequencies, then I can obviously use different frequencies on each tower and I'll be done, right? but I want to use as few frequencies as possible, right? 7 different frequencies, let's say, if I have, then I have to answer, is it enough? Are 7 frequencies enough? Are 7 frequencies enough for me to be able to set up 100 towers? Okay. Obviously, to each tower, I have to allot a frequency, right? So obviously, each tower uh, is allotted a frequency. Okay. So I only have 7 frequencies. Can I use 7 frequencies to um, set up to set up 100 towers and allot frequencies to them? We want a rule which will help us decide if this is possible or not, given a set of um, positions and towers. Okay, how would we decide? Given you know all the distances, how would you decide? So that's the question, right? Given you know all the distances and all the all the mutual distances, what will be a rule to decide if 7 frequencies are enough? And maybe your rule your rule should also maybe tell um, then what's the minimum number of frequencies required.
Okay. Okay. Did like the color is kind of using on the and is it something like
No, it's not. So it's not about the color on the edges. Okay, let's frame the question. Let's frame the question like this. Let's frame the question like this. If these 7 different frequencies, you can think of them as 7 different rooms. Okay, and 100 towers you can think of as 100 subjects, 100 courses, some university, huge number of courses. 100 subjects are 100 subjects are there, and you only have 7 rooms, 7 classrooms. Okay, and if two subjects overlap in time, right, if two subjects have even a bit of overlap, then you have to hold them in different classrooms. Then the question is, if I tell you which pair of subjects overlap, I'm not telling you, but I'm saying that if there is an input where you know which pair of subjects overlap, you can just maybe take an example and try to decide. Okay, you can take a small example with 10 subjects and some overlaps on your own and decide. If two subjects overlap, which is here it corresponds to if two towers are less than 100, right, if two towers are less than 100 distance apart, then they overlap because they cannot use the same classroom, they cannot use the same frequency. You see, it's the same question as that, just framed in this different way. And then that question we have seen, we have not solved it completely, but we have seen it. But in any case, those who have not seen it also just try this version. Okay, so you can easily break this question to that and then do it. You can obviously just break it here directly in the sense that what you can say is that, okay, if two towers are less than 100 meters apart, then I draw a line. If two towers are, so I'll make a graph. Okay, if two towers less than 100 distance, less than 100 meters, and I'll draw a line between them. Draw a line. Yeah. Yes. Yes. It's of no use. Meaning, no. Then you have to give them different frequencies. Right. No. I'm saying if two towers. No, I'm not saying all the towers are less than 100 distance, right? No. I'm not saying that all the towers are less than 100 distance apart. I'm saying some will be 100 less than 100 distance apart. Some of them might be not. Right? Yeah. No. So that is the yeah. So the thing is that if you know it, so the information is not given, but it is given that it is given that, I mean, let's assume that the information is given to you. Then what would be a rule that you will use to decide? And that rule should not depend.
then the circular radius would be it has further it has any points and all.
And that is a special case. That's right, but that is a very special case. Okay. No, the thing here is that if you are given all the information, then what rule would you use to decide it? To decide whether 7 are enough or not? You have to find a good rule which will work for any combination of, for any type of information that is given. Okay, without actually trying all the possibilities, there will be exponentially many possibilities. Is that right? Okay. So that's what an algorithm means, right? When they ask you to find a rule, or when there's a game going on, the two players are playing, then you have to find a rule, you have to find a strategy, right? Which will be, work, which will work regardless of the situation. Okay, so you have to find a strategy which will decide how to figure out the smallest number of towers needed. So sorry, smallest number of frequencies needed, or smallest number of classrooms needed to hold the subjects. That will not have a fixed answer, but your rule should give the right answer in any situation. Okay. Yeah, we'll pick this up. We'll pick this question up. This is a new type of question, but it's a very relevant question. So you can think about them. Think about this. Okay, so I mean, I was framing it in the graph theory language. The graph theory language, it means this, that if two towers are less than 100 distance apart, so this is just, I am saying, just to model the problem in terms of graph. I'm not saying I don't know which two towers are, but I'm saying that if two towers are less than 100 distance apart, then draw a line between them, right? And then what do I want? I want to color the vertices so that if two points are joined by a line, then they get different colors. Isn't that the question? Right? If I make this graph where I join two points which are less than 100 distance apart, which are more than 100 distance apart, I don't join them. This is just the rule. When the input comes, I will, according to the input, I will make my graph. It will depend. The graph will depend on the input, but my rule is fixed. With this rule, I will draw the graph. If two points are less than 100 distance apart, I'll draw a line between them. And so I'll get this big, rich picture. Okay. Now my question is just, I want to give color to the vertices. I want to give frequencies to the vertices. And if two of them have a line between them, then I'll give them different frequencies. So it's basically a question of color the graph with minimum number of colors. It reduces to the chromatic number question, which we had started at one point, but we never didn't answer in detail. Okay. So this is what we'll take up the next time. Okay. And for those who have seen, it's the same question as the interval scheduling question which we were doing the last time. What's the minimum number of machines needed to run all the n processes? It's all of them are the same questions, and we will answer them at once in the next time, and then that will be good. Okay. All right. Okay. And this is also some CMI entrance question. This is some I think old question, but yeah. CMI MSc Computer Science. But this is just an Olympiad question. This is just in some sense. Okay, that's it. Yeah, thank you. Any questions? Anyone has questions?